Hello everyone, my name is Vidal, and today I'm going to present our recent work on improving CauDEr, which is a causal-consistent reversible debugger for Erlang. This is a joint work with my PhD student Juanjo. We both belong to the Valencian Research Institute for Artificial Intelligence at the Technical University of Valencia, Spain. So let me first briefly introduce CauDEr. As I said before, this is a causal-consistent and reversible debugger for Erlang. Well, I think that the notion of reversible debugging is very intuitive. So in our debugger, you can explore a computation in the standard forward direction, and if at some point you see some incorrect behavior, then you can start undoing the steps. That is, you can start going in the backwards direction and try to find what is the cause or the source of this error. Okay, so I think this is a very intuitive idea. But extending this idea to the context of a concurrent language is not so easy. So in particular, let us consider some typical client-server application, okay, in which we have a number of clients, say C1, C2, and C3, that perform mostly independent actions, okay? So the actions of C1 has nothing to do with the actions of C2, etc. So in this context, if we consider a standard or forward computation, and at some point we see that one of the clients, say C2, performs some incorrect action, or we observe some incorrect behavior for this client, we don't want to undo all the actions of this forward computation, because many of these actions performed by C1 and C3 are typically completely independent of the actions of C2 and completely independent of the error or the incorrect behavior that we observe. Therefore, here we use the notion of causal consistent reversibility introduced by Danos and Krivin in 2004, which means that we don't need to undo all the actions in exactly the same order, but every possible reversible computation is correct, is acceptable, as long as it's causal consistent. And causal consistent means that we cannot undo any action until all the actions that depend on this one have been previously undone. Okay? I think this is quite an intuitive idea. It means that we cannot undo the sending of a message until the reception of this message has been undone, or we cannot undo the spawning of a new process until all the actions of this process have been undone. Therefore, in the context of the application that I was mentioning before, in this particular computation, we will ask the debugger to only undo the actions of C2 and those actions that depend on the actions of C2. But every other unrelated action will not be considered. And that's very good from the programmer point of view, because one can focus on the actions of the process that produce some incorrect behavior. Okay. So as for the motivation of this work, initially, some 5 years ago, we considered CauDEr for our developments. CauDEr is the intermediate representation used by by the compiler, by the Erlang compiler. It's similar to core Haskell in the case of the Haskell of the functional language Haskell. So we consider CauDEr both for defining the standard and the reversible semantics, that is for our theoretical developments, and also for implementing our debugging tool. And the reason is quite obvious, because the syntax of CauDEr is simpler than the syntax of the source language. Unfortunately, later we discovered that that was not such a great idea from the point of view of the programmer. And the reason is quite obvious. I mean, this is a source Erlang program, and this is the corresponding translation to core Erlang. Well, as you can see, there are some similarities, but also many differences. So we are introducing a number of constructions that are not present in the original code. So basically, instead of equations, we have just one big lambda expression. We introduce a number of let expressions that you cannot see in the original code. applications are explicit, etc., etc. Okay, there are some additional default cases. So that means that if the programmer writes the code in the topmost part of the slide, and we show this code in our debugger, well, this is going to be very confusing for the programmer. And this is even worse if we consider a large application. Okay. Therefore, the motivation for this work, was to move from core Erlang to Erlang, both at the theoretical and at the implementation level. So in particular, we have redefined all the semantics involved in our approach, which is the standard semantics, logging semantics. This is a slightly extended version of the standard semantics in which we produce a log of a computation. And this semantics is used in order to define a replay approach to debugging, in which the forward computation is not driven by the user but driven by a log that is computed from some previous execution. And then of course the reversible semantics and what we call a control semantics that, well, I will explain what is the role of these control semantics later. So in doing so, we have also considered a number of extensions. Okay, in particular, we have added some additional features that were not considered before, like higher order functions, conditional sequences, etc. We have integrated the two previous approaches. User-driven means that it's the user that decides what is the next action when following a computation in the forward direction. So essentially, the user decides what is the process that should perform the next action. And a replay approach that is based on using a log, as I was mentioning before. So we have integrated now these two approaches. And finally, we have also redesigned the user interface of our debugger, and well, hopefully now it's closer to, it's more intuitive for the programmer because it's closer to the interface of the standard debugger of Erlang. Okay. Now let me show you some technical details of our approach. As I said before, we consider the functional and concurrent programming language Erlang. Concurrency in this language is based on message passing. Okay, so at runtime we have a number of processes that can only interact through message sending and receiving. There's no shared memory. We also consider that communication is asynchronous. Each process has a unique identifier that we call the bit of the process, together with a local queue, okay, which is a sort of mailbox, where messages delivered to this process are stored until they are consumed by a receive statement. And well, we introduced this notion of system, which is essentially a representation of the state of a running application. Okay, so it includes the current state of each process together with a representation of the network. I will show you some details later. So I'm not going to describe the sequential component of the language because it's a typical eager functional language. So let me just focus on the main concurrency features. Here we have spawn, which is a built-in function that creates a new process as a side effect and returns the fresh bit of the new process. Okay. Self, it's a very simple built-in function that returns the bit of the current process. This expression with this exclamation mark, with this operator represented by an exclamation mark, is used to send a message. So the first argument is the bit of the target process, and the second argument is the value, the message that we want to send to this process. Okay. So this message will eventually be stored in the local mailbox of the target process, and the evaluation of this expression returns the value that we are sending. And finally, we have a receive expression. Syntactically, it's very similar to a case expression, but in this case, we try to find a message in the local mailbox that matches any of the patterns in the branches of this receive expression. I will show you an example in the next slide. Okay, and when there's no such a message, then computation suspends. Okay. So let me show you a very simple example in Erlang. This is a sort of minimal client server in Erlang. Here we assume that the initial process is the client, okay, and it starts with a call to function main, and main performs two actions. The first one is spawn, so we create a new process. Let's call this new process the server, and this new process will evaluate this with the start by evaluating this expression, a call to function server with an empty list as argument, which somehow represents the initial state of the server. Okay, so spawns returns the PID of the new process, the server, and then we pass this value to a call to function client. Okay, spawn is asynchronous, which means that we create the new process as a side effect, but we continue with the call to function client. Well, you can see function client here. The definition is, I think, very intuitive. It essentially sends three messages to the server: add paper, add pencil, and self take. Okay, the first two messages are, well, quite simple. And in the last message, you can see that we have a first argument here in this tuple that is a call to function self. And this is a typical construction when we want to get an answer back from the server. Okay, so we send our own PID. This is what the self returns. Okay, so this construction is essentially a simulation of asynchronous communication, because we send a message and we keep waiting in this receive until an answer is sent back from the server. Okay, and if you look at the server, it's essentially an endless loop. Okay, that is waiting for two different kinds of requests. So it could be add item or take. If the request is the message that arrives to the server is of the form add item, then we just add the new item to the list, and we call recursively to function server with the new updated list. Okay, and if the message is take, then we use the first argument, which is the PID of the client. Okay, to send an answer back to the client. In this case, we send the element on top of the list. Okay, and then again we have a recursive call to function server with the remaining elements. So this is a very simple client server in Erlang. Okay, so this is the syntax of the language that we consider in this work. Okay, well, you can find the details in the paper. So let me just mention what are the main differences with respect to our previous approaches to reversible debugging, where we consider core Erlang instead. So on the one hand, we have sequences. A sequence have this form. Okay, and evaluation proceeds from left to right. Okay, so we evaluate E1, then we evaluate E2, etc. And the complete sequence is reduced to the valuation of En. Okay, and we also have pattern matching equations that have this form. In this case, we first evaluate the expression in the right hand side, E, to some value, and then we perform pattern matching between the pattern P in the left hand side and this value V. Okay. Another novelty are conditionals or if clauses, which are sort of a special case of a case expression. Okay, and finally we have higher order functions that were not considered before. Okay, this is how we formalize the notions of process and system. A process is a tuple of this form, where the first component is the PID of the process, the second component is the current environment, which we represent by means of a variable substitution. The next component is the expression to be reduced, and we often denote it in these ways, where C is a context and R is the next regex to be reduced according to typical eager functional semantics. And the last component is a stack that we represent by means of a list. So a system is then formalized in this way, is a pair gamma pi, where gamma is a multiset of triples of this form. Okay, so basically a multiset of messages that we represent by means of a triple with the PIDs of the sender and the target processes, and then the message. Okay, the value of the message. And this gamma is called the global mailbox. Okay, and it models both the network and the local queues of the processes. Okay, observe that we don't have a component to represent the local queue in each process, but this is part of gamma. This is represented by gamma too. And then the second component, pi, is a pool of processes where processes are composed using this operator, okay, which we consider it's a commutative and associative operator. And therefore, an expression like this one is used to denote an arbitrary process P in a system. Okay, before moving on, let me say a few words about the design of word semantics. So the semantics is defined in a hierarchical way, so we have different layers. In the first layer, we define the semantics of expressions, both sequential and concurrent expressions. And on top of that, we have a second layer where we define the semantics of systems. Okay? And the nice thing of this design is that in order to introduce a new semantic, say a login semantics or a reversible semantics, we don't need to change everything. Okay, so we can produce a login semantics by only replacing the rules that define the semantics of systems, but we don't need to change this part. Okay, well, a login semantics is essentially a standard semantics that produces a log of the computation as a side effect that is then used by the replay debugger. Okay, in order to replay a particular execution. And similarly, we can define a reversible semantics by only changing this layer, but we don't need to change anything in this part of the semantics. Okay. Well, the reversible semantics is in principle non-deterministic, which is what we call an uncontrolled reversible semantics. And in our debugger, we have one more layer, which is what we call this control semantics, which is where we have the rules that takes the request from the user, requests like go forward until the sending of this message or go backwards until the spawn of this process, and then takes this information and drives everything in this semantics. Okay, let me show you a hint of the different semantics that we define in this work. Well, and particularly I will focus on the differences with respect to the previous work. So regarding the standard semantics and the evaluation of sequential expressions, the main difference is that now we need to introduce stacks. Okay, that was not needed before. And the reason to introduce stacks is that now we consider sequences. Okay, so let me explain the point with an example. Consider, for instance, an expression like this one, case, some function call of and a number of branches. Well, this is a legal expression. But if we perform one unfolding step, okay, the next expression to be reduced is this call, we might get a sequence of expressions. I mean, the right-hand side of function f may contain a sequence of different expressions, okay? However, this is not a legal expression anymore, okay? So in our small step semantics, this intermediate expression where we have case and a sequence of expressions is not a legal expression, okay? It's not legal. Because in the Erlang syntax, the argument of a case expression must be a single expression. Okay. Therefore, our solution is to move the context, this part in this case, to the stack. Okay, so that we can now perform the unfolding of the function call, and even if we get a sequence, that's not a problem because this is the only expression that we have in our process, and we keep reducing this sequence until we get a value, and once we get a value we can just get back the context and resume computation. Okay, so this is a well, more or less standard strategy, and we have to do the same also for case expressions, because we have a similar situation, because a case expression can also be reduced to a sequence of expressions, and actually also for conditionals, right? So you can find more details in the paper about that. And well, regarding the evaluation of concurrent expressions, there are just some minor changes with respect to previous approaches. For instance, this is how we evaluate, how we reduce a call to function spawn. Okay, so we had to do that at two levels, as I mentioned before. So we have two layers, one at the level of expressions and one at the level of systems. So we have two rules for every concurrent feature. So for a spawn, we cannot do anything at this level, okay, because I mean we need to see the complete system. Therefore, what we do is to label the step with all the required information. We also replace the call to spawn. We reduce the call to spawn to a fresh variable, kappa, sort of future, okay. And with all this information, it's the next layer of the semantics that the rule that reduces systems, okay, where everything is visible. So at this level we can perform the corresponding side effect, which is adding a new process, and we can also bind this variable kappa to the corresponding pid of the new process. Okay, so these two rules cooperate in this way, and we have similar pairs of rules for sending a message, receiving a message, etc. Okay. As for the reversible semantics, the main difference with the standard semantics in our previous approach is that we introduced two new components to each process, omega, which is the log of the process, okay, and h, which is what we call the history. And well, this is essentially a list of items with enough information in order to undo each computation step of a derivation, okay. And well, the definition of a system is essentially the same. So in this work we have slightly changed these definitions, okay. So now a process is defined in this way. We only have a history, but we don't have a log. So the logs are now a global parameter of a system, okay. And this change was required in order to integrate the two approaches to debugging, to reversible debugging. The user-driven approach, where it's the user that decides what is the next action in a forward computation, and the replay approach to debugging, where the next action is determined by the log of a previous computation, okay. So well, this is how it looks like. So we have now two rules for every concurrent feature. So for receive we have one rule where the log is empty, and therefore we have to select any arbitrary message from gamma, okay. So this is an arbitrary message in gamma. And we have a second rule where the log is not empty. So if the current log says that we have to receive the message with this identifier, with this label L, this is the only message that we can receive. And if this message is not in gamma, we cannot perform this step, okay. So we have, as you can see, we move information from the log to the history, and this is the opposite, the rule in the opposite direction. So when we go backwards, we have to move information from the history to the log, okay. Well, you can find the details in the paper. I just want to mention that we have integrated both approaches, user-driven debugging and replay debugging, okay. And then the main change, as I mentioned before, is that now the logs must be a global parameter of the system, okay. Well, finally we have the control semantics, and as I said before, well, at this level the user can introduce a number of requests, like go forward or backwards one step, or go forward up to the sending of a given message, or go backwards up to the sending of a given message, etc., etc. And well, the steps must be causal consistent, so one step forward might imply some more steps in other parts of the system, but this is transparent for the user. And well, you can find the formalization of these semantics in the paper, okay. Let me conclude by mentioning several possibilities for future work. So we would like to add support for more Erlang features, okay. Well, ideally we would like to cover the complete language at some point. Secondly, and this is quite challenging, we would like to deal with distributed applications in which the source code of some of the modules is not available, okay, and therefore we cannot instrument these modules. And well, this is something that we need to do in the current approach. Next, we would like to implement a new, more efficient version of the tracer. The tracer is the tool that instruments the source code of a program, so that its execution produces a log as a side effect of the execution, okay. We would also like to port different extensions that were developed for the old version of the debugger to the new one, and so forth, okay. And thanks for your attention.